Hello all. So in the previous topics like the sequential logic circuit and as well as about the SR flip-flop, we have discussed about the fundamentals that is required on the design of circuits and as well as what is the difference between a combination and sequential logic and what is a flip-flop is and the first type of flip-flop SR flip-flop, that is called as your set reset flip-flop. In other words, it is also called as your reset and set flip-flop, RS flip-flop. We have studied about that. So, but whereas for the input combinations of your S and R to be equal to 1 and 1, when both set and reset is equal to 1, then your Q bar, okay, that is called as your output, and the complementary of the output is in an indeterminate state. We can't determine what it will come. On some instant it may come some value, but whereas on some instant it may come some other value. So we can't get an exact value of what it will get published at the output of an SR flip-flop. Okay, so a flip-flop has been done in such a way that flip-flop is called as your JK flip-flop, which can rectify the drawback that exists in your SR flip-flop, that is the indeterminate presence of the indeterminate state when both R and S are 1 and 1. Yes, now we shall go into this. So the first and foremost thing that we want to look into this is the uncertainty in the SR flip-flop can be eliminated by providing a feedback. Okay, as shown here. Earlier, an SR flip-flop will be having just four NAND gates will be there. That four NAND gates are used. They say, for example, 1, 2, 3, and 4. There will be a cross coupling between your output, input, and everything. But whereas, what is the change that has been made on SR flip-flop to on the SR flip-flop to remove the uncertainty of that is, so this is your SR flip-flop in which your J and K is given as fed as input to two AND gates, okay, to two AND gates, wherein the Q bar is given as an input to the AND gate which contains J input, and the Q is given as an input to the AND gate which is having K as your input. So now this is called as, for the S and R, your input will be your J into Q bar, and for your R it's called as your K into Q. And here this is called as your clock. And we are having two signals, that is called as your preset and clear, which is used to reset and preset the earlier existing values. Your output is your Q and Q bar. And your truth table of this JK flip-flop is when your input 0 and 0, 1 0, 0 1 and 1 1. That is your 0 0, 0 1, 1 0 and 1 1. So your output is equal to output of the next state is equal to, here for 0 and 0, your output is equal to Q1, which is called as your memory state, or the previous state, no change occurs. Whatever the output of the previous state will be maintained. But whereas for your 1 0, your output is equal to 1, and for your 0 1, the output is equal to 0, and for 1 and 1, your output will be toggling. Okay, your output will be toggling. Say for example, in the previous state before this 1 and 1, if your input is your 1 0, that is called as your 1. So here it will become as 0. Okay, that is called as your toggle output. Okay, here a simple RS flip-flop is converted into a JK flip-flop. An RS flip-flop is converted into a JK flip-flop by using two AND gates and a feedback from the output of your Q and Q bar. Now the JK flip-flop, the complete NAND implementation diagram is given here. Here we are having four NAND gates G1, G2, G3 and G4, and here also the cross coupling happens. In the previous SR flip-flop also we had two NAND gates in which the output will be coupled to only G1 and G2 alone, but whereas here in this JK flip-flop the output is coupled to both all the four. Okay, for the odd numbered NAND gates, your Q bar is fed as an one of the input, and for the even numbered NAND gates, your Q is fed as an input. Okay, one of the input. And this is the logic diagram of your JK flip-flop, which has your J and K as your input, and this is called as your clock signal, which is an edge. The flip-flop is an edge triggered device, and this your preset and clear signals, and Q bar is the output and its complementary. So we need to know what is called as an race around condition. Okay, we need to know what is an race around condition. what is the need why we are coming for this JK flip-flop is, as of your SR flip-flop is about when the inputs are 1 and 1, when the inputs are 1 and 1, your output is an indeterminate state. We can't decide the output. So in order to eliminate that, we are coming to this JK flip-flop. And what the change that has been made in the JK flip-flop is, in your SR flip-flop, this output cross coupling will happen only to this G1 and G2 NAND gates, but whereas here it happens for these NAND gates too. So that is, your output is cross coupled. Okay, your Q bar is coupled with your G1 and G3, and your Q is coupled to your G2 and G4. So race around condition, assume the propagation delay, okay, of the flip-flop is your T. Okay, flip-flop is T. If we have J and K is equal to 1, we can see that the duration of the clock pulse is your TP. The output will oscillate back and forth between your 0 and 1. At the end of the clock pulse of the Q is uncertain. So here, if the clock pulses keep on changing, we can't predict what will be the output. Okay, so that condition, that is called as your toggling condition. This can be avoided if the time, okay, if the time is, okay, the time is between your TP and as well as your T. If your time is in between, your time is greater than TP but less than your T. So time is called as your, this capital T is the time period for one clock cycle, that is your both for the positive and as well as for negative. So this is difficult to ensure this inequality because of small propagation time. The inside the ICs and all, the propagation delays are very small, which will be microsecond. So what is a race around condition is, the race around condition is the one when your J and K both input is equal to 1. We can see that the duration of the clock pulse TP, the output will oscillate. Okay, the output will keep on toggling from your 0 to 1 and 1 to 0, 0 to 1, 1 to 0, like that. It will be like the celebration lights, okay, which you used to keep on and off, right? So like that it will happen, which is the oscillation between your 0 and 1s. At the end of the clock pulse, the value of Q is uncertain. Okay, at the end of the Q, it cannot be, even the toggling can also be till T it will be toggling, and after T it will be decided fixed to a particular value, that also we can't determine. Okay, and this can be avoided when the time T is in between your TP and as well as your T, and this is difficult to ensure this inequality because of the very small propagation delay, because the propagation delays mainly will happen in microseconds. And master and slave type of J flip-flop. See, as of you know that as we discussed, it is having an race around condition happens. So that is called as your toggling of your output happens. Okay, between the time period of your 0 to capital T, which is the time period of one clock cycle. So to remove that, what we have done is the time period small t should be in between. Okay, small t should be in between your propagation type TP and your total time period of one oscillation, which is called as your capital T. So the master and slave flip-flop is used, okay, to eliminate the race around condition. This consists of cascaded two SR flip-flops with feedback from the output. Okay, with the feedback from the output second slave to the input first master. A positive clock pulse is applied to master and inverted clock is applied to slave. So for the master, it is having two SR flip-flops, in which the for the clock number 1 and for the first flip-flop will be having one clock and second flip-flop will be having one clock. So for the first one, the clock is given directly, and for the second, it is called as your inverted clock. That is called as your opposing clock. Opposing clock means inverted clock is given. Okay, so here for the first one it's given as positive, means for the second flip-flop it will be given as your inverted clocks. Works like a negative edge triggered flip-flop, but it's actually a pulse triggered flip-flop. Okay, when the clock is high, master is on and slave is off, and hence even if QM changes, Q will not be affected. Okay, when clock is low, master is off. Okay, the slave is on, QM will be positive to Q. Changing Q value won't affect M because master is off. See here. See, for example, this is your master and slave type of flip-flop. So here it depends on the clock. Here the clock, this is your master and this is your slave. The clock is directly given to the master, but whereas the clock is inverted to give it to the slave. See, for example, here two conditions are there. When the clock is 0 and your clock is 1. See here, when the clock is high, master is on. Okay, when the clock is high, your master is on. Your master is in on condition, but whereas your slave is in off condition. So if your QM is passing through this slave also, your Q won't get affected because this slave is off, right? And whereas next one, when the clock is low, master is off, your slave is on, QM will be passed to Q. Changing the value of Q won't affect the M because master is off. See, for example, here if your clock is 0, okay, your clock is 0 means your master is off, but whereas your slave is on. If your slave is on, your Q will be passed to, okay, your slew Q will be passed to the master, but this won't affect the overall output because since your master is off. Here we can say that when clock is high, your master is on, slave is off. This QM will not cannot change Q. Okay, QM changes, Q will not get affected. But whereas clock is low, master is off, slave is on. Okay, master is off means slave is on here when clock is low, because see here the clock is an inverter clock, right? When the clock is zero means this will be off. Then when the clock is given to an inverter, it will be 1, right? So your slave is on. But whereas your clock is 1, your master is on. But whereas when it is negated, it will become 0. Here your slave will be off. If your master is on, your M will be positive to here. Okay, but whereas it won't change the Q because your slave is off. When your clock is 0, your slave will be on. Your output change won't affect the master because master is already off. So that is what given here. Hence, race around condition can be avoided. The race around condition, that 1-1 condition, could be avoided using this type of master and slave configuration. See here, we are using 2 SR flip-flops conveniently to make it right. And now we are coming into the important aspect of the truth table realization and your characteristic table, state diagram, and excitation table. In the earlier session of your SR flip-flop, I've given some gist about how to get the characteristic table drawn. Okay, so for example, your J, Q, and J, K, Q are your inputs. Okay, so J, K, and as well as your Q are your inputs, and Q next is your next output. Okay, what we are going to do is, this JK is called, this is the logic diagram, and this is your clock JK, and Q and Q are your outputs and its complement. So now, earlier I've explained with the help of this diagram of how to get filled this characteristic table in SR flip-flop. Now I will help you, I will guide you to use the state diagram to fill this. See here, Q is equal to 0 and Q is equal to 1. Q is equal to 0 and Q is equal to 1. So this trans you make it as this your 0 0, both sides your Q is equal to 0, and for as well as your Q is equal to 1. For Q is equal to 0, you write your 0 and 1. 0 0, the binary values your 0 0 and 0 1. And for your JK also, and 0 and 2, 0 0 and 1 0. And here the transition from your 3 to 4, okay, 1 0 and 1 1. And here your 1 to 4, okay, 0 1 and 1 1. See here, from this how we can infer this, or from this how we can draw this is, when your input is 0 and 0, okay, J and K is 0 0, Q is also 0, Q is also 0. Now the next state is also 0, so only it is running around here 0 0. The current state is also 0, the next state is also 0. But whereas next one, when your input is 0 1, okay, when your input is 0 1, and your Q is also 0, the next state is also 0, it is retained here. But whereas when you see this 0 0, okay, 0 0, when it moves to, okay, when it moves to 1, okay, when it moves to 0 0 and your Q is 1, okay, Q is 1 means then the next state is also 1, that is called as your 0 0. Your Q is 1 and your next state is also 1, 0 0 moves to this, okay, your Q is 0 0 1, okay, 0 0 1 moves to your 1. And how this could be drawn is, okay, how this could be analyzed is, so see, let me take the value of your 0 0 and 0. Your input is 0 0, okay, and your outputs are your 0 Okay, your output is your 0. 0, 0 and as well as your 0. Now how we can decide is this 0 will come to this and as well as to this, right? 0 and 0 is here, okay. Only 1 0 is here, so 0 means you will be getting that's your 1 here, and here 0 and 0, so here your output will be equal to your 1. Your output will be equal to your 1. Now what we can do in the next thing is, so this is called as your 1. Now this 1 will be coming here, this 1 will be coming here again. See here, this 0, okay, the 0 is given here. This 1 into 0, what you will be getting, that's called as your 0. When it's inverted, it's called as your 1, okay. Now this 1 will be taken here, now this 1 will be taken here. Already here 1 is here, 1 into 1, okay. When both the inputs are same, your output, okay, when both the inputs are same, 1 and 1 input, your output will become as 0. That is what given here, like the same we can take this 1 1 and 1, okay. Your input j is 1 and your k is 1 and your output is your 1, okay. That q value will come to here also, okay. When only one input is there, here the output 1 is given, means here the output is 0, and here what we can do is that 1 is also coming here, right? So when both the inputs are, both the inputs are 1 and 1, both the inputs are 1 and 1, your output is equal to 0. So here also 0 and here also 0. Now this 1 will come to here, right? 0 into 0 and 1, both are different, right? Both are different means both inputs are 0 and 1, both the inputs are different inputs, so your output is equal to 1 here. So that output 1 will be taken to this place, and here already 0 is there. 0 in 1 joins means then the output of this will be your when then 0, and here the output is also 0, output is also 1, okay. Output is also 1, so you can write it as your, this will be your 1, that's your 1 1 and 0. Hence for clarity, so for your 1 1 and 0, the output, that next state is called as your 1, okay. Like this you can analyze for anything, okay. 1 0 0, okay. For your 1 0 0, you take your, this is 1 and this is your 0 and this is your 0. That 0 will come to here also. 0 and 0 means this will become as your, okay, 0 and 0 means your 0, and this is called as your 1, and this will be your 1. And here also for and here your j is your 1, right? This will become as 0, okay. This will become as your 0 because 1 is given as input, means it will become as 0. But whereas your 0, okay, and this is also your 0, right? So this will become as your 1, okay. Now this 1 and as well as your 0, 1 and 0 means both will get, means so you will be getting this 1 here, okay. 1, and that 1 will be given to here, and that 1 will be given to here. Here 1 is given as input, here output already you are getting this your 0. 0 in 1, okay. 0 and 1 means your output will be equal to your 1. So see here for 1 0 0, your output is equal to 1. For any combination, first fix your j, k and q, okay. Push this q to these two gates, okay. When any input is given, single input is given, means this will act as an inverter. When two inputs are given, you know the truth table of a NAND gate. Use the truth table of the NAND gate. First compute this value, first compute this gate value, and take that input to this gate, and then find the q value. You will get exactly this. And how to draw the excitation table for this is, for the 0 0, okay, for the q and q next. For your 0 0, you are getting the 0 0, and for your 0 0, you are getting the 0 1. Here one input is 0, but the other input changes from 0 to 1. So for your 0 0, it should be your 0x. And whereas for your 0 1, okay, 0 1, here it's your 1 0, and for your 0 1 it's called as your 1 1. That means one input is same, but the other input changes from 1 to 0, 0 to 1. So it could be written as your 1x, okay. And next we are 1 0, okay, 1 0, and here also 1 0. For 1 0 it's 0 1, and here it's 1 1, okay. So what you could do here is, so here your 0 to 1 first input wrongly, it changes from 0 to 1. So you could write as your x1, okay. And for your 1 and 1, okay, for your 1 and 1, you can write it as your, for 1 and 1 it's 1 0, and for another 1 and 1 it's called as your 0 0. So that it can be written as your x0. Okay, so that's all about the characteristic equation and of characteristic table and as excitation table. As of characteristic equation is about, what you want to do is just you are going to find the characteristic equation for the q next, right? You can go with an three variable gamma, well and good. Or else if you are good enough in boolean algebra solving, means for in the q next one, where what are how many ones are there, 1 2 3 and 4. So here for the first one it's called as your j bar k bar and q. Okay, j bar k bar and q. And for the second one it's called as your j k bar q bar. Okay, j k bar q bar. And for your third one, j k bar q, j k bar q. And for your fourth one it's called as your j k q bar, j k q bar. You adjust this. Okay, so in this first two things you can take k bar q in common, so j plus j bar. And here in this you can take your j and q bar in common, so your k bar plus your k. So your output is equal to k bar q plus your j into q bar. This is your answer. And thanks for listening to this. And we can very well easily write the characteristic table, state diagram, characteristic equation and excitation table. And the state diagram is more and more needed, because when we go for the state reduction, these tables are more and more important. And when you know this characteristic table, drawing the state table is also a very easy task. When it's 0 0 and q is also 0, it retains at the same state. When you're 0 0, your q is your 1, means it is going to the next state. When it's 0 1, okay, when it's 0 1, if it's on the same statements, it can retain. When you're 0 1, okay, 0 1, it goes to the next state also possible. Okay, so like this you can able to draw with the help of the characteristic table. Thanks for listening. Thanks.